Now that we have the fundamental theorem of calculus under our belts, we're going to really get into integration. In the next section, what we're going to be studying are some basic integration formulas and learning to use what we learned with the fundamental theorem of calculus. We're also going to apply it to something called the net change theorem. With this theorem, we think of the integrand as the rate of change of some function, so that when we're done, what we're getting is the net change of that function from the original value, capital F of A, to the ending value, capital F of B. This, of course, is using the definite integral. We'll be using both definite and indefinite integrals. I'll give you a table which has many of the common integration formulas again. Remember that although they're given in terms of the indefinite integral, you can still use them to evaluate definite integrals, since you need the antiderivative function in order to evaluate a definite integral. Do recall that there are differences between the definite integral and the indefinite. The indefinite integral gives you an antiderivative function up to a constant of integration plus c. The definite integral gives you a finite real number, which represents the area between the curve and the x-axis over that closed interval in the limits of integration. Again, this is net area. Let's take a look at the learning objectives for this section. We have 4 basic learning objectives. First, we're going to go over the basic integration formulas. We're going to explain the significance of the net change theorem, thinking of that integrand function as a rate of change of something. Then we're going to use the net change theorem to solve some application problems, in other words, word problems. Then we'll take a look at the integrals of odd and even functions. Remember that odd means that it's origin symmetric. If you replace x with negative x, you get the opposite of the original function. These are functions such as x cubed and sine of x. Even functions are ones where if you replace the variable x with negative x, you get the same function back. These are functions that are y-axis symmetric. Functions like x squared, x to the 4th, or cosine of x. We're going to take a look at what happens when we integrate an odd or an even function on a symmetric interval that includes the origin, say from -4 to 4. We'll get some interesting results that may help you to simplify some of your calculations. I'm going to go ahead and share my screen with you so we can get started. I've again reproduced the table of basic integration and derivatives that I first showed in the antiderivative section 4.10. Again, if you integrate a constant, you can think of it as the constant times x to the 0. So you get the constant times x up to the constant of integration. The second row gives us the power rule for integration. Add 1 to the power, divide by the new power. Don't forget the constant of integration. This works for everything except 1 over x, or x to the -1. You have that, it's natural log of the absolute value of the argument, which you can see here in the next line. The integral of e to the x dx is e to the x plus the constant of integration. Next, we have a series of trig integrals. The antiderivative of cosine is sine. And this tells us that the integral of cosine is positive sine x plus the constant. When we look at the integral of sine, it can be a little confusing, but remember we're looking for the function whose derivative is sine, and that would be negative cosine plus the constant of integration. The integral of secant squared of x dx is tangent of x. Integral of cosecant x cotangent x dx is negative cosecant of x plus the constant of integration. Remember that when we take the derivative of secant, we get secant tangent. So the integral of secant tangent is secant plus the constant of integration. And finally, when you integrate cosecant squared of x dx, you get negative cotangent of x plus a constant. The next ones that we see are the inverse trig formulas, arcsine, arctangent, and arcsecant. We'll actually work with these more in a later section, section 5.7, where we'll show more easily how we can get different values. We'll look at some that have a formula where the constant may not necessarily be 1, the variable expression may not necessarily be just x squared. So we'll look at, well, more general formulas for the last 3. You need to memorize all the ones from here up. I expect my students to know all of them except the inverse trig functions. Let's go ahead and apply some of these basic integrals to solve some examples. In example 1, we want to find a definite integral of the function x squared minus 3x over the interval from 1 to 3. Using what we've learned from the Fundamental Theorem of Calculus, this tells us that we need to integrate x squared minus 3x with respect to the variable dx between 1 and 3. Applying the power rule for integration, I get x to the 2 plus 1 divided by the new power 3 minus 3x to the 1 plus 1 divided by the new power 2, and it needs to be evaluated between x equal 1 and x equal 3. We're choosing, in this case, the antiderivative function that you see here with a constant of 0. That's not necessary, but when you substitute the upper and lower limit of integration and subtract, any constant would cancel out. So it's easier just to choose the antiderivative function where the constant's already 0. I can rewrite this as x cubed over 3 minus 3 halves x squared, and evaluated between 1 and 3, I can then write this as 3 cubed divided by 3 minus 3 halves times 3 squared minus, and then I can open up and write 1 cubed divided by 3 minus 3 halves times 1 squared. Simplifying each one, 3 cubed divided by 3 is 3 squared, or 9. And in the next, I end up with 3 cubed over 2, which is 27 halves. In the next one, remember that I have to distribute the negative, which is the part of the Fundamental Theorem of Calculus, after I have subtracted the 2 terms, which was a part of the antiderivative function. This gives me 1/3 minus 3 halves. I can go ahead and get a common denominator by multiplying the first by 2 over 2 and the second by 3 over 3. And this gives me 2/6 minus 9/6, which gives me a negative 7 over 6. When I have subtracted a negative 7 over 6, it actually adds it. And this gives me 9, which is 18 halves, minus 27 halves, plus 7 over 6. This gives me a negative 9 halves plus 7 over 6, which I can rewrite the first one by multiplying by 3 over 3. And this will give me negative 27 over 6 plus 7 over 6, which gives me a final value of negative 20 divided by 6. Now, there's another way of substituting in these values. I can also reduce my final answer, and I should, to negative 10/3. There's another way that you can substitute rather than substituting both limits of integration into both terms. You could instead just work with the first term, substitute the upper and subtract the lower, and then subtract the second term, substituting the first and then subtracting the lower. The other way of writing this is instead to substitute the upper and lower limits of integration in place in the first term and pull the 1/3 out. This would give us 3 to the third, which is 27, minus 1, which would give us 26/3. Then in the second one, we factor out the minus 3/2 and then again substitute the limits of integration in place of the x squared to get 9 minus 1, or 8. The 8 divided by 2 was 4, so this gives me minus 12. Now I need a common denominator, which would be 3 divided by 3, and my common denominator is 3. So I end up with 26/3 minus 36/3, which gives me a negative 10/3. Note that I got the same solution, which I should have. I find the second method somewhat simpler because I like factoring out the fraction or constant at the front and then substituting the limits of integration into each term. Both are correct. You can do it either way. Choose the method that makes the most sense to you. Now that we've got this value, let's take a look at the picture and see what we're finding. In the picture, we have the graph of x squared minus 3x, and over the region from 1 to 3, I've shaded the area. In this case, it's all below the axis, all negative, and it is equal to negative 10/3 square units of area. And we can add square units onto our solution. Now let's take a look at the next example in our video, which is example 2. In example 2, we have an indefinite integral of the square root of x minus 1 divided by the square root of x. Again, I have the difference of 2 terms, which means I can split the integral across each one. I can also keep them together and integrate one at a time. In order to integrate, it would be better to go ahead and rewrite this one with rational exponents. Remember that the square root is the 1/2 power. Rewriting this, I get the integral of x to the 1/2 minus 1 over x to the 1/2 times the differential dx. Then I can use the rules for exponents to move the x to the 1/2 from the denominator to the numerator by changing the sign of the exponent. Now I'm ready to integrate, finding the antiderivative function using the power rule. The only time I can't apply the power rule is if the power is -1. That results in the natural log of the absolute value. In this case, applying the power rule gives me x to the 1/2 plus 1, which I'll write in fraction form as 2/2. This becomes divided by the new power 3/2. The second term becomes minus x to the minus 1/2, again, plus 1 in fraction form, and dividing by the new power. Don't forget, you have to add the constant of integration because this one is an indefinite integral. You need to end back up with the variable x, and we have to have a plus c. Now I'm going to go ahead and clean this up and rewrite it. Dividing by a fraction is the same as multiplying by a reciprocal, which means that I can write this as 2/3 x to the 3/2 minus 2 x to the 1/2 plus a constant. You could rewrite it in radical form, but honestly, I probably would just leave it in the previous form. But you could rewrite it. And this would be our solution, an antiderivative function, the same variable as in the original integral, up to the constant of integration plus c. Let's now take a look at the next example. And it looks like I forgot to share my screen with you, so let me do that now. All right, moving on. We have one more example before we talk about the net change theorem. In our next example, we again have a definite integral from 0 to pi of sine of x minus cosine of x. We want to find a number answer which represents the area between the curve sine x minus cosine x and the x-axis over the closed interval from 0 to pi on the x-axis. In order to do this, we're going to think of it as the integral of sine x dx minus the integral of cosine of x dx. We're going to write it in one combined form, and then we're going to apply the antiderivatives of each trig function individually. In this case, the integral of sine of x is negative cosine of x. Remember that this function has to be the function whose derivative gives you back the integrand. And the derivative of negative cosine is positive sine. Then we have a subtraction, and we want to think about the integral of cosine of x dx. When we think about this, we need a function whose antiderivative gives us this. So the antiderivative of cosine, so we're looking for the function whose derivative is cosine, which is sine. This is a definite integral, so we're going to evaluate between x equals 0 and x equals pi. In order to evaluate, I'm going to follow the second method since I think that one is actually a little bit simpler, and it will allow me to factor the -1 out of each individual term. In this case, I get negative times the cosine of pi minus the cosine of 0. Then I factor the negative out of the second term, and I substitute the limits of integration. Sine of pi minus the sine of 0. Once I have this, then the next thing I want to think about is evaluating the trig values. The cosine of pi is a -1, and the cosine of 0 is 1, so I get -1 minus 1, or -2. But it's inside parentheses with a negative on the outside, so I end up with 2. On the second one, sine of pi is actually 0, and sine of 0 is also 0. So I'm subtracting 0, which tells me I have 2 square units of area between the x-axis and the graph of sine x minus cosine x. It doesn't mean that all 2 square units are above the axis. It means the net area is 2 square units. Let's take a look at the graph now and interpret our result in light of the graph. When we look at the graph, you can see the function sine of x minus cosine of x graphed here in red. The region between 0 and pi, I've shaded the area between the curve and the x-axis. Notice there is some area that's below, and there's area that's above. The net area is 2 square units. The blue shaded area must be more than 2, because after subtracting the gray shaded area, we end up at 2. Let's now turn our attention to the net change theorem. The net change theorem considers the integral to be a rate of change. In other words, the integrand itself is the derivative of something, which of course we know that it is. It is the antiderivative function's derivative. In other words, lowercase f. And what it says basically is that when a quantity changes, the new value equals the initial value plus the integral of the rate of change of that quantity. So we can express the formula in 2 ways, and pretty much they're both just a restatement of the Fundamental Theorem of Calculus, part 2, the part we like the most. The net change theorem says that if you interpret the integrand as the derivative rate of change of a function, in this case, the derivative of the antiderivative, you can then interpret the result as giving you the new value of that function, uppercase f, equal to the original value of the function plus the integral of the rate of change. But we could also just write it in terms of what we had in the Fundamental Theorem of Calculus Part 2. The definite integral from a to b of f prime of x dx is f of b minus f of a. If you were to subtract or add f of a from both sides here, you would get the formula that you see here. They're equivalent formulas, so which one you apply just depends on what you're looking for. The significance of the net change theorem is in the results. We can think about net change to area or velocity or position, just to name a few of the applications. Let's now take a look at what we did when we studied this in section 5.2 when we were looking at velocity. When we're looking at a velocity and we're integrating the velocity, we end up with the total displacement or the net displacement. Remember, the net displacement is actually the definite integral, which we now have a new way to calculate. The total displacement is the definite integral of the absolute value of the velocity function. This gives us the change in position, if you will, since we can think of the velocity as the derivative of position. In that way, we can think of this as a net change in position. In order to apply this, we're going to use the Fundamental Theorem of Calculus Part 2. Let's suppose that we want to find the net displacement, which would be the integral of the velocity function, which is the integral of the derivative of the position function. And we want to find the total distance traveled, which would be the integral of the absolute value of the velocity function, both over the interval from 0 to 2. Again, what we're thinking of here is that we're integrating the velocity function with respect to time, but we're thinking of the velocity as actually the derivative of the position function. In this way, we can think of it as a rate of change of position, and what the Fundamental Theorem of Calculus gives us is the net change in position. Let's now take a look at finding the net displacement. The net displacement in this case is going to give us the integral from t equals 0 to t equal 2 of 1/2 times e to the t minus 2 with respect to t. It is a definite integral, so we're looking for a definite number. This number will represent the net displacement from the origin or the original starting place. So when we look at this and we want to integrate, remember that we can split this and think of this as two integrals, 1/2 e to the t dt minus the integral of 2 dt. 1/2 and the 2 are constant factors which can be pulled to the front. Both of these would be evaluated between 0 and 2. This will give us 1/2, and we need the antiderivative function for e to the t dt, which is e to the t. And now we need to apply the power rule. We can think of the minus 2 dt as minus 2 t to the 0th power dt, which gives us minus 2t. This is to be evaluated between t equals 0 and t equals 2. In the next, I'm going to factor the 1/2 off, and I'm going to substitute the upper and lower limits of integration into each term. In the second term, I factor off the -2, and I simply substitute in the limits of integration in place of t. This is going to give me 1/2 of e squared minus e to the 0. E to the 0 is not 0, it's 1. So this gives me 1/2 times the quantity e squared minus 1. And then I have over here -4. I could go ahead and multiply everything out so that I can combine the constant terms. This would give me 1/2 e squared minus 1/2 minus 4. And since 4 is minus 8/2, this would give me 1/2 e squared minus 9/2. Remember that e is a number. And this definite integral represents, in our case, net displacement. So this would be the displacement of the object, the change in position from where it was originally. And again, we're thinking of the integral as the derivative of position rather than just the integral of velocity. But velocity is the derivative of position. So our change in position is 1/2 e squared minus 9/2. Let's take a look at that graph. In that graph, you can see that we have the function 1/2 e to the x minus 2 graphed, and I've shaded the region between 0 and 2. This represents the motion of the particle. This is the velocity on the vertical axis and time on the horizontal. And we can tell that we have a net displacement that is negative, meaning that it must end up on the negative side, which would be, well, west or south of wherever it started originally. If I approximate the value, I get about negative 0.8055 meters. In other words, it's that far from the original origin. Let's now take a look at reworking the problem, but looking instead for total displacement. This is not where it ends up compared to where it started. This is instead, what's the total distance traveled? Remember, if you start in Denver and drive to Colorado Springs and come back, your displacement is 0 since you end up where you started. But your total distance traveled is about 160 miles. We want to apply that now to this one. When we're looking at this part, we need to take the absolute value of the velocity function. We are again integrating from 0 to 2, but we're looking for total displacement. And because we're looking for total, we take the absolute value of 1/2 e to the t minus 2 dt. Now, in order to figure this out, we really kind of need, well, the graph, because we have to know when it's positive and when it's negative. Remember that the definition of the absolute value is that you leave it alone if it's greater than or equal to 0, and you apply a negative if it is less than 0. We need to know when this graph is above and below the axis. In order to do that, we're going to take this value here and set it equal to 0 and solve. So we're looking for the t-intercept. To find the t-intercept, we're going to set the integrand without the absolute values equal to 0. By isolating the exponential term, I can get it rewritten finally as e to the t equal to 4. I need to know what the t value is when that happens, so I switch to logarithmic form. This tells me that the natural log of 4 is equal to t. The natural log of 4 must be on the graph, this location that you see right here, where it crosses the t-axis. from 0 to the natural log of 4, it is below the axis, which means that I need to multiply the integrand by a -1. From the natural log of 4 to 2, it's above, so I can leave the integrand function alone. Again, we're applying the definition of the absolute value. I'm going to split the original integral into two pieces. The integral from 0 to the natural log of 4 and the integral from the natural log of 4 to 2. I know that when I go from natural log of 4 to 2, it's already positive. So I can simply leave the function alone. For the first one, however, I cannot leave it alone. Because it is below and I need absolute value, I multiply both terms by a negative. This will make the exponential term negative and the 2 positive. This means that I can rewrite this integrand as 2 minus 1/2 e to the t dt. This will force it, in a sense, to, well, flip up and cause that displacement to be positive. Now that I have this, we go ahead and integrate each piece. This will give me 2t minus 1/2 e to the t, evaluated between 0 and the natural log of 4, plus 1/2 e to the t minus 2t, evaluated between natural log of 4 and 2. Go ahead and pause the video, substitute these values, then turn the video back on so we can compare our results. This is a rather tricky one to solve algebraically because of all the exponentials and natural logs. When you substitute, you get 2 times the quantity natural log of 4 minus 0, which gives you 2 natural log of 4. Factor off the minus 1/2 and then substitute the limits of integration in place of t in the exponential. E to the natural log of 4, well, e to a power and natural log undo each other, so you just get 4 minus 1/2 times 4. The second one becomes e to the 0, which is 1, so you get minus 1/2 times -1, which is a positive 1/2. The second one, you're going to factor out the 1/2 again and substitute the limits of integration in place of t in the exponential. This gives you e squared minus e to the natural log of 4, which is 4 again, resulting in 1/2 e squared minus 1/2 times 4. Finally, in the last term, you're going to factor off the minus 2 and then substitute the limits of integration in place of t. This gives us -2 times t2 minus natural log of 4, which gives us minus 4 plus 2 natural log of 4. Now we need to combine like terms and try to interpret our result. We have two natural logs of 4, which gives us 4 natural log of 4. And combining some of the other constants, I end up with minus 15/2 and plus e squared. This turns out to be a positive value, which I was expecting since I forced everything to represent positive displacement. This tells me that the total displacement of the object over this travel was 1.74 meters approximately. Let's now work through another example of applying the net change theorem to find this change by integrating a rate of change of a function. In example 5, we want to write an integral that expresses the increase in perimeter of a square when the side length s is increased from 2 units to 4 units, and then we'll evaluate the integral. Now, obviously, we could just simply write the box and compute it by hand, but we want to learn the method of using calculus to solve these problems. So the first thing we need to do is come up with a formula which relates perimeter to the side length of a square. In this case, since all the sides are the same length, the perimeter is a function of side length s, is 4 times s. Now we want to find the rate of change of this function. It's the perimeter that's changing. We find the derivative with respect to s is 4. This is going to serve as the integrand function. Now we need to find the limits of integration. The limits of integration are measuring the change in the independent variable, which is s. We start with the side length of 2 and we end with the side length of 4. In other words, it's changing. In this case, we're going to integrate the rate of change of perimeter from 2 to 4. Finally, we evaluate the integral. When we integrate, remember that we're replacing the rate of change of perimeter with the 4 as the integrand. When I integrate 4, I get 4s, and I evaluate from 2 to 4, giving me a value of 8. That means that the change in the perimeter is going to be 8. Let's take a look at a picture and see if we can interpret what actually had. When we started, we had a square which was 2 units on each side, which means that the perimeter was equal to 8. After we increased the lengths of the sides to 4 on each side, we add them together to get a revised perimeter of 16. And the change is 8. Between the 16 it ended up and the 8 original. And remember, this is the ending value, f of b, minus the beginning value, f of a. And this gives us the 8. Let's now do a similar problem where we're not given exactly the units of change. We want to write an integral that quantifies the change in the area of the surface of a cube, 3-dimensional object, when side length doubles from s units to 2s units. We're not told what s is, only that it's increasing from s to 2s. This means we'll need a dummy variable probably inside of our integral. In this case, what we're going to do is we're going to first find the formula for the surface area of a cube and relate it to the side length s. In order to do that, go ahead and draw the image of a cube. After drawing the image of the cube, go ahead and label the sides and think about what the surface area of the whole thing would be. I have 6 sides, the 4 sides around the box and the top and the bottom of the box. Each side is the same, s wide, s long. And that means that each side is s squared in area. And there are 6 of them. So my relationship is 6s squared. Now I'm looking for net change in the area. So I need to find the derivative of the area function. When I take the derivative of the surface area with respect to the side length, I get 12s. I'm going to use the 12s inside of my integral as the integrand. But because I know that my original value is from s units to 2s units, I'm going to change my variable of integration to a dummy variable. I chose t. Choose x, happy face, star, whatever you like. It is awkward to have this be s and ds and have the limits of integration also be s values. So we use a dummy variable instead. This, of course, is just a polynomial integrand, so we can apply the power rule. When we apply the power rule, we increase the power by 1, and we divide by the new power, which is 2. We need to integrate and substitute the limits of integration, s to 2s. This gives me 6t squared between s and 2s. I'm looking for the change in the surface area. In this case, what I'm going to do is substitute by factoring off the 6, and I'm going to substitute 2s in place of t and square it, and then substitute s in place of t and square that. This will give me 4s squared minus s squared, which gives me 3s squared times the 6 I factored out, or a net change of 18s squared units. Let's think about what happens if we have actually changed the cube. Let's go ahead and imagine our original cube, which is here. If we're finding the surface area, we know the surface area is 6s squared. We've already calculated that. If we increase each side length so that we've doubled it, then this means that we can recompute the surface area by taking 2s on each side and finding the area of each of the 6 sides. The area of one side would then be 2s times 2s, which would give us 4s squared. Now we have 6 sides. So the surface area of the larger cube is going to be 6 times 4s squared. And this comes out to be 24s squared. Now, when we're looking at this, what is the net change? We found the net change to be 18s squared. Take 24s squared, you subtract the original 6x squared, you do get a net change of 18s squared. Let's now shift our attention from rates of change and instead talk about integrating even and odd functions. This section does help you to calculate integrals, can make your work much shorter and much simpler. However, I would not call it an absolutely necessary thing to learn. You can still integrate without knowing these rules and be just fine. But if you know them, it can shorten some problems pretty dramatically. Let's take a look and remind ourselves of what even and odd functions are and what they mean. Remember that to test for even or odd symmetry, we replace the independent variable with its opposite, x with negative x, or t with negative t. These two functions that you see graphed here, sine of x and x cubed, are odd symmetric functions, also called origin symmetric. This is because if you replace the x with negative x, you do not get the original function back. Instead, you get the opposite. You take a negative x and cubed it, you got negative x cubed. And the sign of negative x is negative sine of x. What this means is that if you fold it twice, once on each axis, the graph will lay on top of itself, meaning that on the graph, if we change the value of x, say from 1 to negative 1, then we have to change the value of the y as well. That's what we mean by origin or odd symmetry. Let's now take a look at the even symmetric functions. In the even symmetric functions, we have y equal to x squared and y equal the cosine of x. These are both even symmetric functions, also called y-axis symmetric. In other words, if you fold on the y-axis, these graphs lay on top of themselves. If you fold down the vertical, you will get that they lay directly on themselves. In an even symmetric graph, if you replace the independent variable with its opposite, you get the same function back. In other words, if you're looking at the value of, say, 1, 1, and you change the value of x from 1 to negative 1, it does not change the y value. Y value stays the same because the function stays the same. What we want to think about is what would happen if we were to integrate one of these functions across a symmetric interval containing the origin. For example, let's think about trying to integrate this function over the section from -2 to 2. We'll take a look at the sine of x. If I want to integrate over the closed interval from -2 to 2, notice what happens. I have this area here, which corresponds to the exact same area here, since it doubles it. And I have a little negative section here, which is repeated over here. It doubles it. For an even symmetric function, integrating across a symmetric interval that contains the origin gives us twice the area. Let's now take a look up here at the odd symmetric function. And I'll take a look at sine of x. And for this one, we're going to go between -π/2 to π/2. When I'm looking at this region here, I'm thinking about the area that is above the axis and the area that is below the axis. When I think about those two areas on an odd symmetric graph, notice what's happened. I have the same amount of area above as I have below, which means my net area is 0. If you integrate on a symmetric interval containing the origin or an odd symmetric function, you get 0 net area. Again, the symmetric interval must contain the origin and go from -2 to its opposite, 2, or from -π/2 to its opposite, π/2. Must be the same number on both sides, but with opposite sign. Let's now take a look at this in integral form. If we have an even function such that if you replace the variable x with -x, it doesn't change the function, you end up with double the area. What you can do then is, instead of integrating from -2 to 2, you can integrate from 0 to 2, half of it, and double the area. Because it's a symmetric interval, it will give you the same value. If you have an odd symmetric function where you replace the variable with -x and you get the opposite of the original function, then integrating from -a to a gives you 0 net area. This works for functions because of the type of symmetry that they have. So when we're looking at something like this, which has even symmetry, we can see that because it's even symmetric, if we're integrating across a symmetric integral or interval containing the origin, then we know that we have the same amount of area on the left as we have on the right. So we can, instead of integrating from -3 to 3, integrate from 0 to 3, which means we don't have to substitute a negative value, and then double the area. And for odd functions, again, this is working because of the type of symmetry, creating a positive area on one side and a negative area on the other that are identical. In this case, when you integrate from -2 to 2, you get 0 net area. Let's now take a look at examples 7 and 8 and apply this theorem. First off, if you forget to apply the theorem, you can still integrate using the Fundamental Theorem of Calculus. It's going to work and give you the right result. It's just that these theorems, well, shorten your work to practically nothing. Let's see how to apply it. When I look at this first one, I notice, first of all, that x to the 4th is y-axis or even symmetric. When I see that, I look for the interval over which it's being integrated. If I have an even interval on both sides, and I do because it's from -2 to 2, then I can instead write this as double the integral from 0 to 2 of x to the 4th dx. And then when I substitute, I won't be substituting a negative value, which does help a little bit. In this case, we apply the power rule, increase the power by 1, divide by the new power, and then we evaluate between 0 and 2. I like to factor off the constant and then do my substitution. In this case, I would get 2/5 times 2 to the 5th minus 0 to the 5th, which gives me 32 minus 0. And when I multiply, this gives me 64 over 5. Now, the 64 over 5 represents the area between the graph of x to the 4th and the x-axis between x equal -2 and 2. This is, of course, square units. Now we want to take a look at the next example. In this case, we want to test, do we have symmetry? When we look at this one, I'm first drawn to the fact that both powers are odd numbers. And I see that I have a symmetric interval which contains the origin. So I'm suspicious that perhaps this has odd symmetry. I'm going to test for odd symmetry. When I test for odd symmetry, I'm going to replace the variable x with -x. This gives me -x to the 5th power plus a -x, which I can rewrite as -x to the 5th minus x, and factor out the -1 to get -1 times the original function. Note that this function, x to the 5th plus x in parentheses, matches the original integrand. Once I recognize that it has this origin symmetry, I know that integrating on a symmetric interval containing the origin will give me 0 net area. There's really no work to work out. You simply write the result down, that you get 0 net area. Now, could you work it out instead using the power rule? Yes, of course you can. And you will get exactly the same result. It's just that, well, it's shorter if you don't have to do that. We've now reached the end of this section on net change. It's a relatively short section. Our next video is going to deal with one of the most important sections in the entire course, called U substitution integration. This is another one of those techniques that you have to master at a 95% level or above. When you start Calculus 2 on day 1, you have to be good at U substitution because it gets used all the time. I hope you'll join me for the next video where we explore how to integrate when we have composition in the integrand function.